Bismillahirrahmanirrahim. Today we will discuss a new electronic device which is known as the transistors. Okay, transistor. So transistor is one of the very important electronic device which is used in almost all the electronic circuits. Okay, so we have different types of transistors. Okay, I will explain about it. So we have different types of transistors. One is bipolar junction transistors, okay, bipolar junction transistors, and we have the field effect transistors, okay. So the transistors, actually the bipolar junction transistor is usually known as BJT, and this is usually known as FET. Actually this FET is again we have many types, that is we have JFET, that means junction field effect transistors. This J for junction, okay, junction field effect transistors, and another one is the MOSFET, okay, that is the metal oxide, that is MO. This MO is showing actually metal oxide field effect transistors. But basically in this course actually we will deal mainly about the BJT. This you will study in electronic circuits 1 in very detail, electronic circuits 1, okay. So that you will be seeing in electronic circuits 1. So we will first talk about the BJT. So bipolar junction transistors. So what is this? Bipolar junction transistors, or generally known as BJT. All of you know that a diode is having actually two regions basically. That means it is having a P type and an N type, okay. That means it is connected, it is actually having a P type and an N type semiconductor, okay. This is the notation of a diode, okay. But a BJT, basically bipolar junction transistor, is having actually three regions, okay. It is having three regions. That means you have a three regions, that is one of the possible case is you can have a P type semiconductor here, N type here, and a P type again here. So this kind of transistor is known as PNP transistors, okay. These are all BJTs. Then another type possible is so you have three connections also, see here, okay. You have three connections. The another kind of connection which is possible is another kind of configuration which is possible is N type here, P type here, and N type here, okay. And this is another connection. So you can see here there are three regions. So this kind of transistor, is usually known as NPN transistor, okay, NPN transistor. So there are basically three regions and three connections, okay, for this device, okay. So there are three connections, three regions, and how many junctions are there? Can you tell me? In a PN junction diode you have a junction here, this is a junction. Similarly like this you have a junction here, you have a junction here. So there are two junctions, okay, two junctions. So this is the basic configuration of a BJT, okay. Since we have two types of BJTs are available, I told you, because we have two type of configuration possible. One is a PNP and another one is the NPN transistor, okay. So we have two types of transistors, that is PNP and NPN, okay. Now we will see what are the different what are the names for these pins, okay. So you can see here, I will draw a little bit, okay. This is the emitter, this is the base, and this is the collector. Anyway, I didn't introduce this term. So you have three connections. One can be a p-type semiconductor or an n-type semiconductor. N, P, N. Okay, so I told you there are three regions, and one is N, another one is P, and another one is N. So this region we usually call this terminal or this region as the emitter. So this one is usually the emitter. Then another one, this connection at the center, which is known as the base. Okay, or the center region, we usually call it as the base. Okay, and the last one, actually this is known as the collector. Okay, this one. Okay, this is the collector, and this pin is the collector pin anyway. So we have three regions. So we have three regions. One is the emitter, the another one is the base, and another one is the collector. Okay, collector. So you can see here we have three different regions. Now, one of the important application, what are the application of these transistors? So one of the important application is it can work like a switch. It can act as a switch. Okay, it can act as an amplifier. Okay, so these are all the basic two applications of the transistor. There are many applications. Okay, so we will talk about all these things later anyway. Now I want to tell you one thing. What is the symbol for the transistor? Symbol. Okay, you know that for the diode, actually for the diode you have a symbol something like this. Okay, now for the transistor you have a symbol which is like this for the NPN transistor. Okay, and you have another kind of symbol which is shown like this, which is for the PNP transistor. Okay, you can see the direction of the arrow mark is different in both of these figures. So we have two different, one is the NPN transistor and another one is the PNP transistor. So different symbols. These are all the symbols, and the symbol for the diode is shown above. Okay, now we have different modes of operation. I told you we have three different regions. Also we have three different regions. Suppose I consider a NPN transistor. This is the emitter, usually call it as E. This is the base, and the another one is the collector. Okay, so I have different possibility. I can actually, if you have a semiconductor PN junction, you can give two type of power supplies. As you seen, we can give either forward bias or reverse bias. Okay, we can have two kind of biasing. So if I can connect this thing in the forward bias, or I can connect it in the reverse bias. Okay, another thing, another connection possible is I have the base emitter region, base collector region. Here also I can either forward bias or reverse bias. So based on the forward bias or reverse bias at emitter base, you see here I am talking about this region. So this is emitter and this is base. So this region we will call it as the emitter base region. Okay, emitter base region. So at emitter base region, or we can say another region, here you can see this region between the base and the collector. This is known as the collector base region. So, or collector base region. Okay, so we can actually forward bias or reverse bias at emitter base region and collector base region. Okay, so based on it we have different types of configuration. So I will first of all I will explain about this configuration. We can either so suppose you have an emitter base region and this is the collector base region. Okay, now First of all, if the emitter base region, if I am giving forward bias to the emitter base region, and if I am giving the reverse bias at the collector base region, and now we will call the mode of operation as active mode. Okay, this is known as active mode. So we will come to very detail about this later. And the application, it's very important. Application, it's a amplifier. Okay, in amplifier actually we will be using like this. So what is an amplifier? Amplifier is used to amplify the weak signal. Suppose you have a very weak signal from the microphone. If you want to make it a signal with large amplitude, then you have to use the amplifier. Okay, so amplifier is such a kind of device which can boost your signal. Okay, now the second part, the second region, suppose if the emitter base region is forward bias and the collector base region is also forward bias, both are forward bias, then this we will call as the saturation mode. That is, both are forward bias. Okay, that means you know that whenever we connect it in forward bias, we have a current actually. So if both are forward bias, your transistor will act like a short circuit, because you know, if you have a diode, if you give forward bias, it acts like a short circuit like this. If there are two ends here, you can see here there are two ends, the emitter base junction and the collector base junction. If you are giving both of them forward bias, both become conductive or both become short circuit. That means your transistor, entire transistor become short circuit. Okay, similarly your transistor become short circuit. So this is like a short circuit. Okay, and this, the one of the main application is the switch. Okay, you know, in a switch you have two conditions, one is on and another one is off. Suppose if a switch is short circuit, you can say it, if you are making a switch by using a transistor, we can use the transistor for making a switch. If you are using the transistor for making a switch, then if the transistor moves to the saturation region, then what will happen? Then both become forward bias and it become act as a short circuit. Now the third one, actually you have emitter base junction as reverse bias and the collector base junction, both are reverse bias. Okay, so what is this? You can see here that if you give reverse bias to a diode, then it become an open circuit. If both junctions for a transistor is reverse bias, that means both junction become open circuit. That means it is in a mode of cutoff. That means it is cutoff mode. Okay, saturation mode and cutoff mode. Okay, this is saturation mode. So cutoff means this is open circuit. Okay, so this again, you know, this is one of the property of the switch. A switch can be a short circuit or an open circuit. So again, the application is switch. And now the last part, we have one more configuration. That means the emitter base junction you are giving reverse bias and the collector base junction you are giving forward bias. Okay, this kind of configuration is known as the reverse active mode, and it is it is having very less gain. Okay, and not used. Okay, it is not used in common practice actually, but we will be using it for some rare applications. Okay, so but you have to remember about these main things, that these are all the main configuration. This main configuration you have to remember. Okay, so how the transistor, what are the different modes of operation of the transistor. Okay, now what I want to tell you is that, first of all, what is the working of a transistor? A transistor has three regions, I told you. So first of all, I will draw the three regions of a transistor. Okay, so I will show here, I have a emitter. This is the connection for the emitter. Okay, emitter, Then I have a small region which is very thin basically. Okay, this I will make it little bit larger. So this is the emitter, this is the base, okay, and this is the collector. Okay, so you have a base and you have a collector. Okay, now we will see the first mode of operation. What will happen if I give this one? Okay, I am talking about this one, emitter base junction. I am going to forward bias. You know what is forward bias? Suppose I am taking a NPN transistor. This is N region, this is P region, and this is again N region. Okay, this is N region. Now you have different regions. So you are considering an NPN transistor. Okay, NPN transistor. Now we will see what will happen. So for the N region, you can give a power supply which is, for the N region you can give negative, okay, and for the P region you can give positive. That means this end, the emitter base junction, is forward bias. Okay, forward bias. Now at the collector base junction, you can connect like this. You can connect, I told you we want to make it which kind of bias? Yeah, it is reverse bias. So the collector base junction, I am going to make it reverse bias. So collector base junction is reverse bias. So reverse bias means, you see here, this is N type semiconductor. I will connect the positive power supply and I can connect to the base like this, but usually we don't connect like this. Okay, we will make the potential at the collector a little bit high, and we will connect everything to a common ground. Okay, so this is the common point, which is the ground. But I told you the emitter base junction is forward bias. In order to limit the current, if there is some current, we have to limit it. Otherwise what will happen, the transistor will carry a very large current and sometimes it may damage also. Okay, so this is the resistance we are going to connect here, and it is known as RB, and this is the base I told you, and this is the emitter. So since we are connecting this power supply at the base, so we will call it as VBB. Okay, since you can see another power supply here, and this is connected, this power supply, this power supply, since this power supply is connected at the collector, you can say that this you can name it as VCC. Okay, that's it. So you have two power supplies, one is VCC and another one is VBB. Okay, and also here also you can limit the current. Is it possible to limit the current? So here also we will connect a resistance at the collector. It is known as RC. So the purpose of RC I will discuss later anyway. Okay, now you can see here we have a power supply VBB and RB. We have another power supply VCC and a resistance RC. Okay, now what will happen? I told you N-type semiconductor. We have N-type semiconductor at the emitter. So at the emitter we have a lot of electrons, right? We have lot of electrons at the emitter. Okay, I will just show the electrons. Now at the base we have P-type semiconductor. So we have a few number of holes. We have lot of holes, but there is very important point I want to tell you is that the emitter has basically emitter has a doping very high. Okay, I am talking about the doping. Doping means it is the process of adding the impurities. So number of free electrons will be very high. So the doping in the emitter is very high. That means it has more free electrons. Now at the base we will see the doping at the base is very low. that means it has only a few holes. Okay, and the last one is nothing but the collector. The doping at the collector is usually moderate. Okay, moderate. That means it has some electrons, have free electrons again, because we are talking about n-type semiconductor here, p-type here, and n-type at the collector. Now that's why I am actually showing only a very few holes at the base. Okay, you can see I am just showing just 3 holes at the base. Okay, just for your understanding. Now at the collector also we have a lot of electrons. Anyway, we have a lot of electrons, okay, at the collector, but it is moderately doped, not like our emitter. Okay, the emitter is very heavily doped. Okay, so you can see that one more thing, that the width here, this is the width of the emitter and this is the width of the base. You can also see I have drawn something here. This is the width of the collector. Okay, you can see that the width of the collector is very high, right? That means the width of the collector is greater than width of the emitter, and the width of the emitter is greater than the width of the base. That means the base is very narrow. Okay, the width of the base is very small. Okay, now we will see what will happen if we give a power supply like this. That means we forward bias the emitter base junction, we forward bias here at the emitter base junction, and we reverse bias between the collector base junction. So this is giving you a reverse bias, okay, at the collector base junction. Okay, now what will happen? You can see here, since you have applied a positive voltage at the base, you will get a positive field here and you will get a negative field here. And you know, because of this, the electrons will be attracted towards the base, right? Because of this positive field. So electrons will be attracted towards the base, and also you can see there is a negative potential at the emitter. Because of this, the electrons will be pushed. The electrons will be pushed away from the emitter connection. You can see here. So the electrons will be moving towards the base. So a lot of electrons will be moving towards the base, but you see here the width of the base is very small, and the doping concentration of the base is very low. As I explained here, it's very low. What will happen? Suppose hundreds of electrons are moving from the emitter to the base. You can see at the base I have just shown only 3 holes. So only these 3 holes can combine with the only 3 electrons can combine with these holes in our case, as we shown here. Now you can see here, as it combines with the holes, it will make a small electron flow in this direction. So electron flow, we have a small electron flow in this direction, as I am showing here. It is because the doping concentration at the base is very small, and because of this, what will happen? Because of this reason, very few number of electrons will combine with these holes here. Okay, only a very few number of electrons will combine with these holes here, and they will constitute a current, and the electrons will be flowing into the positive of the VBB. So electrons will be flowing like this. Okay, electrons will be flowing like this. So you know what is the direction of the current. It will be the direction opposite to the flow of electrons. Okay, now you can see here lot of electrons now reached the base. So electrons are now accumulated at the base. So you can see here lot of electrons reached the base, and a few of them combine with holes, and make a small current. Okay, that means the base current is very small. So the current which is flowing through the base, or the number of electrons flowing through the base, is very less. Usually the current is of the order of microampere. Okay, in many transistor you can see that this current is of the order of microampere. Now what will happen, since there are lot of electrons at the base, these electrons will make a concentration difference between the number of electrons at the collector and number of electrons at the base. Now the number of electrons at the base is very larger when compared to the number of electrons at the collector. So what will happen, these electrons will diffuse. Okay, so this is diffusion, we will call it as diffusion. So it is because of the concentration difference. Okay, so these electrons will diffuse into the collector, and these electrons will reach the collector. So now collector has lot of electrons. Okay, lot of electrons which are coming from the emitter basically. Okay, now you can see here at the emitter, sorry, at the collector, what is the power supply we have given? At the collector you can see we have given a positive power supply, because this is positive. So this is positive, and the charge of the electrons are negative. The charge of the electron is negative. So lot of electrons are there at the collector, and because of this positive power supply, these electrons will move towards the collector, and it will flow through the collector pin, and it will move. So these are all the electron flow. Okay, electron flow. So these electrons will flow through this. Okay, a lot of electrons are flowing through the collector wire, you can see, and it will go to the battery. Okay, positive of the battery. So you can see here lot of electrons are coming. That means electrons coming from emitter will reach the base. It will reach the base, and some of them combine with holes and make a small current, which is known as the base current. Okay, base current. So that's what happening at the base. Now when it reaches the base, lot of electron, they will undergo the diffusion because of the concentration difference, and they will reach the collector. Okay, reach the collector. Whenever they reach the collector, due to the positive field will pull the electrons, and it will make a current. Electrons and make a current. Okay, so that's what happening. So electrons are reaching at the collector. Now I will draw this picture again. I told you we have the emitter, which is another one is the base, and this is the collector. This is N, this is P, again this is N. Okay, now our power supply, positive and negative, and this is like this, and we have a resistance RC, and this is VCC. Okay, now another part is nothing but we have RB. Okay, I am just drawing the figure, and this is the VBB. Okay, that's it. Now I will explain this once again. You have lot of electrons at the emitter, and you have very few number of holes at the base. So electrons, whatever electrons reaching at the base will not make a complete current through the base. What will happen, only a few of them recombine and it will flow through the base. So the majority of the electrons will reach the collector. It will reach the collector, and there is a positive field because of this positive, and it will pull up. You can see here it will be pulling, and all these electrons will be drifting towards the collector pin and it will flow in this direction, electrons will be flowing in this direction, and it will make a current. So this is electron flow. So you can say here, you can see here electrons are flowing like this. Okay, now what will be the direction of the current? You can see here the electron from the emitter is going up, so the current direction will be just opposite. So this current we will call it as emitter current. And you can see here the flow of electrons at the base is towards the positive terminal of VBB. So the current direction will be like this. So it is IB. And you can see here at the collector the current direction. You can see the electron flow is from left to right. So the current direction will be from right to left. Okay, so this is the current direction. Now you can easily write the relation between these currents. What is the relation between IC, IE and IB? So what is this IC? IC is known as the collector current. Okay, collector current. And what is IE? IE is known as the emitter current. Okay, and IB, what is IB? IB is known as the base current. Okay, so we have three different currents. Now what is the relation between all these currents? You can see here, if you apply the Kirchhoff law, you can see here, this is your transistor. Some current, one is coming in, IC is coming in, IB is also coming in, but IE is going out. So IE is equal to IC plus IB. Okay, so this is one of the important relation you have to remember. Okay, so that's how the transistor is working. Now I have already told you that the current IB is very small, okay, and your IE is equal to IC plus IB. Okay, so you can see here this current IC, IE is at the input side. You can see, you can view this side as the input side. Okay, and I will tell you why it is known as input side later. And this side usually known as the output side. Okay, input side and the output side. Okay, now you can see here your IB, you can view it as a input current anyway. So you can view your IB as a input current, and you can view your IC because you are talking about the output here. This is I output. So at this output you have the current IC. This is the current IC. Okay, so you can view IC as the output current. Okay, if you measure this, if you take the ratio of IC over IB, you can see that it is a very large number. It's a very large number, and it is usually a large number. Okay, and this ratio we will call it as the beta. Okay, and beta DC, because we are talking about the DC current. Okay, so this is known as the beta DC. So beta DC is nothing but the DC current gain of the transistor. It is known as the DC current gain of the transistor. Okay, now I will draw the symbols for the transistor. Slowly we will introduce the symbols. So I told you we are talking about the NPN transistor. The symbol was something like this. Okay, the arrow mark is like this. How to remember this? You have an N-type semiconductor. This is at the emitter, and this is the base, and this is the collector. So you have the N-type semiconductor here, you have the P-type semiconductor here, and this is again N-type semiconductor. So you can see here the current will be always flowing from this P to this N. So the direction of the arrow will be like from P to N. That's how you can remember. So now we will connect our power supply. So this is your RB and this is your VBB, okay, and I will connect the emitter to the ground, okay. The same thing, that's what we have seen just now, okay. So instead of drawing these boxes, we will be using the circuit symbol for the transistor, okay. So by using NPN transistor, now you can see here I have RC and I have VCC, and this part is connected to the emitter, okay. So this kind of thing, that means giving the power supply in a proper way, that means giving the power supply, this is known as the, we will call it as the biasing. So we have to properly bias the transistor, biasing, okay. So we have to properly bias the transistor in order to make it operate properly, okay. Now I told you this current which is going outside from the emitter, which is known as the emitter, that means the current is going outside, that means emitting the current, that's why it is known as the emitter. And this current is going inside, that means the collector is collecting the current, that's why it is known as the collector. And this is your base, okay. Now I told you that the ratio of IC over IB, we will call it as beta DC, or I can say my IC is equal to beta DC times IB, okay. So if I can control my IB, I can change my IC also. How to control IB? To control IB, you just need to control the RB, okay. If you change the value of RB, you can see that the IB will be changing, and according to this IB, you will be getting IC. So what is the reason for this? You can see here, if you are considering a transistor, emitter, base and collector, you have seen that lot of electrons has been this is n type, sorry, N, P and N. So lot of electrons has been injected from emitter to the base, and this base current actually from the base, only a few of the electrons escaped from the base, okay, and most of the majority of the electrons has been reached the collector, okay. So the base current IB is very small when compared to IC. So IC over IB will be a number which is very much greater than 1, or it usually have the values 300, 400, etc. okay. How you can control this? You can change this. So, and also we have seen that we have already seen that IC over IB is equal to beta DC, and this is nothing but the gain, DC current gain, okay, DC current gain of transistor, okay. So how you can basically how you can change this guy, that means beta DC, the current gain? It can be controlled by changing the doping, okay. So in the market different types of transistor, different varieties are available with different current gain, okay. So according to your application, you can choose one. So this can be controlled. If you want to change beta DC, if you want to change, then you have to change the doping. So that is the main point, okay. Now you can see here at the collector, lot of electrons are injected from the emitter. Because of this, the collector is having lot of electrons and which is reaching from base to collector by the process of diffusion, and the collector actually it is capturing the electrons, and it is constituting a current by applying a positive field as shown here. So because of the positive field, you can see that all these electrons will be moving towards the collector, okay. a collector pin. So that, and it makes a current. So you can see here, you are actually creating a pump. You can see, you can view like a pump. You are actually creating a pump. You know that if you have something like a water pump, okay, so this is this is water, okay, and this is a pump. What is happening here, okay, and this is the output of the pump. So water will be coming here, right, output of the pump. So you have a lot of water in the tank, and this part actually pumping the water. So this is a pump, and this part is actually sucking the water from here, and it is pumping out as shown here. And you can view this part as a collector, and this is as a collector because this is actually pumping outside, and this water is sucking in from here, and this you can view it as an emitter. Okay, now there is no base here. Suppose somebody is sitting here, standing here, and is controlling something. If he is having a controlling equipment, so that he can control the speed of this pump, okay, or he can control the flow rate of the pump. Now if he rotates this, if he close this, what will happen? The pump will be moving with a very low speed, or you can say with a low output. So according to the you have a control valve, you can say, you can have a control valve here, control valve. So if you control this valve, actually you can control the output. So the whatever which is coming here, you can call it as IC, and whatever input you are going to give for controlling this, we will call it as IB. So what is happening? If you change this thing IB, you can change the IC, and this is your reservoir. Okay, so this reservoir you can actually consider it is having a lot of electrons. So you can consider it as a your power supply, you can say. Okay, so this is how it is working. Or another example I can give, you have a water tank, and you have a connection output. Okay, you have a connection here. Now you have a control valve, and this is the output. So this is at some height from the ground. This is your ground, and somebody is standing here to watch this. Okay, and this is the collector, you can say, and this is your base, and this is your emitter. So what is the idea? If you change this base, you can control the water flow here. That means if you change the base current, you can control the collector current. Okay, so the collector current is actually because of the water which is pumping from the emitter. Actually, lot of amount of water is coming from here. So it is because of the emitter current. So the emitter current, actually the electrons at the emitter will be reaching at the base, and it cannot combine completely, so it will make a small base current, and the remaining electrons will be reaching at the collector. And I told you the base current is very small. Base current is very small, so that you know that IC is equal to beta DC times IB, and this is a constant based on doping. So what will happen? If you change the IB, then the IC will be changing. But how many times? This is a very large number. So suppose beta DC is 300, then it will change 300 times. Okay, so if IB change by 1 microampere, then IC will be changing by 300 microampere if beta DC is equal to 300. So it's very large number. Okay, it has no unit, actually it is just a number. Okay, gain. Now you see here, we have seen lot of equations which are related to the transistors. You have seen here IE is equal to IC plus IB. Okay, and you have also seen IC over IB is known as the beta DC, okay, and it is very larger than 1. For example, it is 300, 400, etc., okay, like this. And there is one more ratio which is known as IC over IE. I told you this relation. What is the meaning of this relation? You can see here from the relation that IC is less than IE. So if IC is less than, because IE is equal to IC plus IB, so IC will be always less than IE. So if you take this ratio, you can see that this ratio will be less than 1, but you can see it is very close to 1, 0.9, 0.98, etc., okay, like this. So it is very close to 1, okay, it is less than 1, but it is very close to 1, because IB is small. The usual value of IB is of the order of microampere, okay, it will be of the order of microampere. So I hope this relation is clear to you. So next we will see the same thing. IC is equal to IC plus IE is equal to IC plus IB. So IE is equal to, what is our IC? I have already told you, beta DC times IB, right? So beta DC times IB plus IB. Okay, this is nothing but beta DC plus 1. I can take IB as common, so into IB. So IE is having another relation like this. Okay. Now I told you this ratio, that means IC over IE, this ratio is having a name. It is known as alpha DC. Okay. So we have alpha DC as IC over IE. Okay. Okay. Now we can see, we can substitute this in this equation 1. So substitute 2 in 1, what will happen? You have, this is IE, which is equal to IC plus IB, and I can say that my IC from this relation, IC equal to alpha DC times IE. So IE is equal to alpha DC times IE. It is nothing but our IC, because I replaced IC with alpha DC times IE. Okay, plus IB. Okay, so what is IB? What is IB? IB is equal to, sorry, I will use the next page. So IE is, I will write the equation again, alpha DC times IE plus IB. Okay, but what is IB? IB is beta DC times IC. Am I correct? Because this is coming from IB is equal to, but IB is equal to IC over beta DC. Sorry for this. So we have IB is equal to, IC is equal to IC is equal to beta DC times IB. Okay, so I will replace this thing. So okay, I will write the equation. This is IB. So this is alpha DC into IE plus, what is IB is nothing but IC over beta DC, and this is IE. Okay, so you can see here the term for IE on both sides. So IE into IE plus, IE minus alpha DC times IE is equal to IC over beta DC. Okay, am I correct? Now you can see here IE into 1 minus alpha dc is equal to IC by beta dc. Okay, IC by beta dc. So what is this thing? Now you can say here IE, I can take this guy here, so IE by IC, IE by IC is equal to 1 by, I can move this this thing to the right side, 1 minus alpha dc, am I correct, into beta dc. But you know that alpha IE over IC is nothing but 1 over alpha, right, because alpha dc is equal to IC by IE. So 1 over alpha dc is equal to IE by IC. Okay, so we can use this notion. So I will rewrite this equation in the next page. So 1 by alpha dc is equal to 1 by 1 minus alpha dc into beta dc. Now I can rearrange it again. I can move this here and I can move this here. Okay, then what will happen? Then beta dc is equal to alpha dc by 1 minus alpha dc. Okay, so this is the relation between beta and alpha. If you know alpha, you can easily find the value of beta. Okay, that's what I want to tell you. Now we can have, so if you know alpha dc, you can find the value of beta dc. Okay, so don't forget the basic equations, that is IC is equal to beta dc times IB, and IE is equal to IC plus IB, and another equation for our beta dc is equal to alpha dc by 1 minus alpha dc. Now how to obtain alpha dc if you know beta dc? So how to obtain alpha dc if you know beta dc? So we will explain this also and wind up this lecture. So we will see here, we have the equation beta dc is equal to alpha dc by 1 minus alpha dc. So if I add plus 1 on both sides, just rearrangement of the equation after adding plus 1, then we will get the answer. So add plus 1 on both sides, what will happen? 1 plus beta dc is equal to 1 plus alpha dc by 1 minus alpha dc. I think this is clear to you. Okay, now 1 plus beta dc is equal to, you can cross multiply here. Okay, so it's become 1 minus alpha dc plus alpha dc divided by 1 minus alpha dc. Okay, a simple fraction. Now you see here 1 plus beta dc is equal to, you can see 1 minus alpha dc plus alpha dc divided by 1 minus alpha dc. Okay, so this is nothing but, you can see this is plus, sorry, this is minus and plus, then it will cancel, become 1 minus 1 by alpha dc. So 1 plus beta dc is equal to, it is equal to 1 by 1 minus alpha dc. Okay, now 1 minus alpha dc. Okay, now you can see, you can rearrange this equation, this to here and this to here. Okay, so 1 minus alpha dc is equal to 1 by 1 plus beta dc. Now we want to find alpha dc. Okay, so I can bring this guy here and I can move this to the right side. So if I bring this term, the term 1 here, and this is the term 2, if I move the term 1 to the left side, it become minus. So 1 minus 1 by 1 plus beta dc is equal to, if I move the term 2 to the right side, it become plus, so alpha DC. Now I can substitute this, I can simplify this, so this become 1 plus beta DC, okay. Then you have to include the minus sign, then you have 1 divided by 1 plus beta DC, that is equal to alpha DC, okay. Now you can see here from the equation, this is minus 1 and this is plus 1, so it will cancel. So beta DC divided by 1 plus beta DC, that will give you the alpha DC, right. So that will give you the alpha DC, okay. So that's how you can get it. Now we will conclude. We have all the equations, basic equations related to the transistors. That is, the first one is nothing but IC is equal to beta DC times IB, okay. So that means if you change the value of IB, the current IC will change, okay. Now we will see more on this later, and IE is equal to IC plus IB, okay. Now IC over IE is nothing but alpha DC, okay. And another equation, that is nothing but beta DC is equal to alpha DC divided by 1 minus alpha DC. And how to find alpha DC? Alpha DC is equal to beta DC divided by 1 plus beta DC. So these are all the main equations which are related to the transistors, okay. So you have seen that if you change the base current, the collector current will be changing, okay. If you change the resistance of at the collector, that means RC, then you can see that the collector current will not be changing at all if the transistor is in active region. That concept we will discuss in the next lecture. Thank you.